You can see it on a clear night, a pale band of light stretched across the sky, faint and silent, like something the universe forgot to clean up. Your brain looks at it and files it away as beautiful, distant, safe. That is the first mistake, because that band of light is not what it looks like. And the moment you actually follow the numbers, something shifts, not dramatically, quietly, the way a door closes behind you before you realize you can't go back. So let's ask a simple question. How long would it actually take to cross the Milky Way? Not approximately, not poetically, actually, because the answer doesn't just describe a distance, it describes a limit. And by the time we get there, you will understand why that limit is a lot more permanent than anyone usually admits. On a clear night, away from city lights, you can see roughly 2,500 to 3,000 individual stars with the naked eye. That sounds like a lot. Our galaxy contains between 100 and 400 billion. What you see on the clearest night of your life, in the best possible conditions, represents less than 0.00001% of what is actually there. The rest are too far, too dim, or buried behind walls of gas and dust so thick that even our most powerful telescopes cannot fully see through them. And that band of light does not look enormous because it is close. It looks that way because your brain cannot process what it is actually measuring. The Milky Way is roughly 100,000 to 200,000 light-years in diameter. 1 light-year is about 5.9 trillion miles. The Milky Way is not one of those, not 10, not 100,000, up to 200,000. Here is the comparison that should stop you cold. If you shrink the Milky Way to the size of the continental United States, from coast to coast, our entire solar system, the Sun, Earth, every planet we have ever visited, every probe we have ever launched, would be smaller than a single grain of sand, not visible to the naked eye, not visible under a magnifying glass, gone, completely gone inside the continent. And it does not stop there. The Milky Way is not a flat, simple disk you could drive across. It is a structure, a rotating spiral with arms that curl outward across hundreds of thousands of light years, wrapped in a halo of dark matter so vast and so invisible that we can only detect it by measuring how it bends the gravity around it. We cannot see it. We cannot touch it. We only know it is there because of what it does to everything else. We are sitting inside this structure right now, about 25,000 light years from the center, embedded in one of its outer spiral arms, being carried around the galactic core at roughly 515,000 miles per hour. That is not a choice. That is just where we are. And even at that speed, one full orbit around the center of our own galaxy takes approximately 225 million years. We have never completed one lap. Not once in the entire history of our species. That is what we are asking about crossing. So let's try. Let's be as generous as possible. Let's take the very best humanity has ever produced and point it directly at this problem. Voyager 1 has been traveling since 1977. Nearly 50 years in space. Right now, it is the farthest man-made object from Earth. It moves at roughly 37,000 miles per hour. At 37,000 miles per hour, pointed directly across the Milky Way, traveling non-stop, never slowing, never breaking down. For the entire trip, it would take approximately 1.7 billion years to reach the other side. Not a million, billion. Let's go faster. The Juno spacecraft briefly reached about 165,000 miles per hour during its approach to Jupiter. More than 4 times Voyager, still irrelevant. The Parker Solar Probe currently holds the speed record for any object ever built by human hands. It uses the Sun's own gravitational pull as a slingshot, looping tighter and tighter until it reaches speeds of up to 430,000 miles per hour. 430,000 miles per hour, the fastest thing we have ever made. At that speed, non-stop, no delays, no malfunctions, no course corrections. Across the Milky Way from one edge to the other, the trip takes approximately 300 million years. And that is assuming nothing fails, nothing breaks, nothing drifts off course. For 300 million years. 300 million years ago, the first dinosaurs hadn't appeared yet. The continents looked nothing like they do today. The ancestors of every living thing on Earth were only just beginning to crawl onto land. Now here is what makes this worse. The Parker Solar Probe reaches its peak speed only because it is falling toward the Sun, using gravity as a free accelerator. In open interstellar space, that advantage disappears completely. There is no star to slingshot around. There is nothing to pull you forward. Whatever speed you launch with is the speed you keep, unless you are burning fuel to accelerate, which means carrying that fuel, which means more mass, which means more fuel required to move that mass, which compounds the problem before the mission even begins. So that 300 million year estimate is not a ceiling. For a ship traveling under its own power through open space, it is closer to a best case. The real number, accounting for the physics of sustained propulsion across interstellar distances, gets worse. Not slightly worse, significantly worse. That is our best technology applied to this problem. It is not enough, not even close. But there is one more option. And for a moment, it almost sounds like a way out. Nothing with mass can reach the speed of light, not because we haven't solved the engineering yet, because the universe will not permit it. To accelerate any object with mass to the speed of light requires infinite energy. Infinite energy does not exist. This is not a gap in our knowledge. This is a statement from the universe itself. But let's push as close as physics will allow. Suppose we built a spacecraft that could travel at 99.9999% of the speed of light. Something extraordinary happens. Einstein's special theory of relativity tells us that time does not pass the same way for everyone. The faster you move, the slower time passes for you compared to people who are standing still. This is not theory in the speculative sense. It has been measured. Atomic clocks on airplanes tick slightly slower than identical clocks on the ground. The effect is real. At 99.9999% of light speed, the factor by which time slows is approximately 700. That means for every 700 years that pass on Earth, only 1 year passes on the ship. Apply that to the 200,000 light-year crossing, and the crew experiences roughly 285 years of travel time. Not 200,000 years. 285. There is also a second effect called length contraction. At near light speed, the galaxy itself appears to compress in the direction of travel from the crew's perspective. What looks like 200,000 light-years from Earth looks like only a few hundred light-years to the people on board. The universe physically reshapes itself around the motion. But here is what that actually requires. To reach 99.9999% of light speed, you need to accelerate continuously. A ship that accelerates at a rate comfortable for a human crew, roughly equivalent to the pull of Earth's gravity, would take about a year of ship time to approach near light speed. That sounds manageable. What it does not account for is the fuel. As a ship accelerates closer and closer to light speed, its effective mass increases. The more mass you have, the more energy you need to push it faster. The closer you get to light speed, the more energy each additional fraction of a percent costs. The energy required does not increase in a straight line. It curves upward steeply, and near the top, it becomes almost vertical. Reaching 99.9999% of light speed would require a quantity of fuel so enormous that no known energy source or storage system comes anywhere close to providing it. On paper, this looks like a solution. It isn't, because we haven't talked about what the journey actually does to the ship and to the people inside it. Interstellar space is not empty. It contains gas, stray atoms, and occasional dust particles. At low speeds, these pass through or around a spacecraft without consequence. At 99.9999% of light speed, they do not. At that velocity, a single hydrogen atom, the most common particle in the universe, strikes the ship with the energy of a high-powered rifle round, not occasionally, constantly, every second, for the entire crossing. A particle the size of a grain of sand hits with the force of a nuclear weapon. Any shielding thick and dense enough to stop this would be so heavy that the energy required to accelerate it to near light speed becomes physically impossible to generate, and any shielding worn down by centuries of particle impacts could fail without warning in the middle of interstellar space, where no repair and no rescue are possible. The radiation alone would be lethal without perfect protection. At those speeds, light from stars ahead gets compressed and shifted upward in energy. Visible starlight in front of the ship shifts into ultraviolet radiation, then X-rays, then gamma rays. The front of the spacecraft would be bathed in radiation that kills unprotected crew within minutes. And then there is time. Even compressed to 285 years from the crew's perspective, that is more than 10 human generations. No one who boards the ship survives the journey. Everyone is born and dies in transit. And on Earth, while those 285 ship years pass, 200,000 actual years go by. Every person who watched the launch is dead within decades. Every civilization that funded the mission is gone within centuries. The entire recorded history of humanity would fit into a fraction of the time that passes on Earth while the ship is still crossing. Consider what that means for the mission itself. The people on board in Generation 3 have never seen Earth. They were born inside a ship, raised inside a ship, and they will die inside a ship. Their understanding of the mission, its purpose, its destination, its origin, exists only through whatever records and culture the previous generation managed to preserve and pass down accurately. And that transfer of knowledge across 10 generations without outside contact, without correction, without resupply, introduces its own compounding risk. Cultures shift, priorities change, records degrade. What begins as a mission of exploration could, after 2 centuries of isolation, become something the original crew would not recognize. Every problem you try to solve creates a new one. Better shielding means more mass. More mass means more energy to accelerate. More fuel means even more mass. More generations on board means more food, more air, more resources, more systems that need to work perfectly for centuries without replacement parts or outside support. The constraints do not cancel each other out. They compound. And there is one more constraint we haven't touched yet, the one that makes everything else irrelevant, because it doesn't slow the mission down. It ends the possibility of coming back. There is a moment in this journey that almost never gets discussed. It happens early, relatively early in the context of the full crossing. There is a point at which the energy required to decelerate, reverse course, and return to Earth exceeds any fuel supply any ship could physically carry. Not because the technology is insufficient, because the math makes it impossible at those speeds and those distances. After that point, returning is not a decision anymore. It stops being physically possible. The crew doesn't choose to continue. They simply have no other option. The mission becomes irreversible, not as a dramatic moment, but as a quiet consequence of velocity and fuel and the unforgiving arithmetic of deep space. And it compounds further. Radio signals travel at the speed of light. If the ship is traveling at nearly the speed of light in the same direction as its transmissions home, those signals take almost as long to reach Earth as the journey itself. Replies to early transmissions would not arrive back at the ship for tens of thousands of years. From an extremely early point in the mission, the crew is completely alone. There is no mission control. There is no course correction from the ground. There is no abort signal. What that silence actually means is worth sitting with for a moment. Every space mission in human history has depended on continuous communication. When Apollo 13 lost an oxygen tank 200,000 miles from Earth, engineers on the ground had hours to devise a solution. When the Mars rovers encounter problems, teams of specialists spend days running simulations before sending a single command. That infrastructure, that ability to diagnose, correct, and adapt from the outside disappears entirely on a near light-speed crossing. Every decision falls to whoever is on the ship. Every system failure is solved with whatever is on board. There is no calling for help. There is no waiting for an answer. The ship and its crew become, from a very early stage, entirely self-contained and entirely alone in a way that no human mission has ever had to be. Just a ship, whatever it launched with, and the compounding silence of interstellar space. Every solution reveals a deeper constraint. Every constraint creates a new problem. Every new problem makes the previous solution irrelevant. And underneath all of it, the distance remains unchanged, unmoved, indifferent. So here is the actual answer. The number is not the answer. 300 million years with our best technology, 285 years of ship time with near light speed travel and time dilation, 200,000 years from Earth's perspective, regardless of either. Those are real numbers. They are scientifically accurate. But none of them are the answer. The answer is this. The Milky Way cannot be crossed the way the question implies, because crossing it requires surviving radiation that kills you, shielding that makes acceleration impossible, fuel requirements that compound against each other at every stage, a point of no return that arrives far earlier than most people expect, and a severance from Earth so complete that the civilization that launched you would not exist in any recognizable form by the time the journey ended. The problem was never distance. It was what distance at this scale does to everything else, to time, to the body, to the mission, to the possibility of return. And once a mission like this passes that threshold, it does not become harder to complete. It becomes impossible to reverse. We live on a grain of sand, inside a galaxy that is itself one of an estimated 2 trillion in the observable universe. Our fastest machine needs 300 million years just to cross the one we inhabit. And the physics that might compress that journey for a crew would silently erase 200,000 years of Earth history in the process. That is not a number. That is the edge of what we can do. And right now, We are nowhere near it.